based on a paper we put out in January. I'll also, if I have time, have a couple of slides on some work that's not yet published, will hopefully come out soon. So the title of my talk is General Gauge Mediation. And when I gave this talk, a similar, longer version at BU, I remember Shelley Glashow said, sounds like a dish in a Chinese restaurant, but okay. I forgot to thank the organizers also for inviting me here to give this talk, and also for organizing this wonderful conference at this amazing place, at this amazing time, at the eve of the LHC era. Okay, so we're all very excited that the LHC is just around the corner. Of course, we've been saying that for a while, but now it's actually coming true. The LHC is just around the corner. I have nothing to add to this other than my enthusiasm, and perhaps one observation that here at CERN, we can really afford maybe to be more precise in our language. The LHC isn't actually around the corner if we're sitting here in the auditorium. It's more across the street. So anyway, I hope you've all had a chance to go and have a look. So what is this experimental apparatus across the street going to tell us about physics beyond the standard model? Well, there are many possibilities, and I guess because there isn't a compelling model out there, we have to make a choice of what to work on and what to talk about. So the choice I'm going to make today is to talk about supersymmetry out of personal taste, and also I do believe I feel it's the most well-motivated candidate for what we might see at the LHC. So suppose we see supersymmetry at the LHC. Well, I think it's safe to say we have our work cut out for us. We know that if supersymmetry exists, it must be a spontaneously broken symmetry of nature, since we haven't seen the superpartners yet. Furthermore, we know from various considerations that if it's broken, it must be broken in a separate hidden sector, so an almost decoupled sector which is separate and distinct from the MSSM, from the world we see around us. And the SUSY breaking, which happens in the hidden sector, must then be communicated to our visible sector via loops of some interactions or some extra particles. So explaining exactly how this works, if indeed we discover supersymmetry at the LHC, there are people that say we're going to discover supersymmetry at the LHC regardless of whether it exists or not. But anyway, when the dust settles, when the dust settles and it becomes clear we have discovered supersymmetry, then explaining how it's broken and communicated to our visible sector will, I think, be one of the great challenges, theoretical challenges for our time. It's going to take a while, probably, maybe not just the LHC, but will require future colliders to really settle the question. So it's going to put food on our tables for many years to come. Okay, so as I said, there are many competing explanations for how supersymmetry is mediated to the MSSM. The one I want to focus on today is just one class of models known as gauge mediation. Again, because I consider it to be a well-motivated choice. So the idea of gauge mediation, of course, is that the fields and interactions which communicate SUSY breaking to our sector are nothing other than the interactions of the standard model, the gauge interactions of the standard model. And the advantage of doing that is, since the gauge interactions are flavor blind, mediating SUSY breaking with them automatically solves one of the big problems of the MSSM, which is the SUSY flavor problem. So the generic point in the MSSM parameter space has drastic flavor-changing neutral currents, which are unobserved. And so explaining why we live in a non-generic point in the MSSM parameter space where there are no additional sources of flavor violation other than those of the standard model, explaining that is one of the challenges of model building, and that's one thing that's gauge mediation solves automatically. So there are other advantages to gauge mediation, and I've just listed them here. I won't have time to explain them, but it's part of the standard propaganda, if you will. Okay, so that's gauge mediation in a nutshell. Now, let me get to the motivation for today's talk. The question we set out to answer was, what are the most general predictions and parameters of gauge mediation? So this is obviously an important question for the LHC era. If we want to rule in or out gauge mediation at the LHC, we have to know what's the most general possibility allowed in models of gauge mediation. So the reason this is an interesting question, or at least to us, was that to date many models of gauge mediation have been constructed. There are thousands of papers on this. But it was not clear to us in looking at all these papers which features of the models that were constructed were general and which were specific. So that's the question we set out to answer. A lot of these models that have been built fall into a framework which is known as ordinary gauge mediation and goes back to the work of these people in the 90s. So this is a very successful framework, and a lot of the predictions for colliders and things that people think of as related to gauge mediation actually follow from this framework. So the idea of the framework is very simple, and it's also similar in spirit to what we want to do today, or what I want to tell you about today. So the idea of ordinary gauge mediation is to throw away all the information in the SUSY breaking sector except to say that there's some field, X, which is really a spurion, so it's really a background field, which only its VEV matters. And this field then gets a lowest component VEV and also an F component VEV. And so the F component VEV breaks supersymmetry, and the lowest component VEV together with the F component VEV tell us that our symmetry is broken. So this spurion is now supposed to parameterize the hidden sector, and it has to communicate SUSY breaking to the visible sector. So we introduce fields called messengers, which they have to be in a real representation of the standard model gauge group in order to couple to the X field via these Yukawa type couplings. And through these Yukawa type couplings, the messengers receive tree level SUSY mass splittings, rather the scalar components of phi receive tree level SUSY mass splittings, and then loops of these messenger fields together with the standard model gauge fields then communicate supersymmetry breaking to the MSSM. So we can see this in more detail. The one loop, at one loop, we obtain gaugino masses. So the external legs here are the U1, SU2, and SU3 gaugino fields of the MSSM, and the fields that run in the loop are the messenger scalars and fermions. And in order to get something on zero, we have to insert both VEV of the spurion lowest component and its F component. That leads to a formula for the gaugino mass, which looks like this. It is proportional to alpha R, the standard model gauge couplings, because it's one loop, and it also involves the SUSY breaking in this dimensional combination. At two loops, we get these fermion masses through these 8 diagrams. Again, the fields that run in the loop are messengers and gauge fields, and that leads to the following formula for this fermion mass squareds. Again, it's two loops, so it's alpha squared. There's an F over M squared that appears here, and then we sum over the gauge groups weighted by this group theory factor, which is a quadratic Casimir. Okay, so based on these formulas and things, people have come up with, explored the parameter space of ordinary gauge mediation. It's still interesting to explore this parameter space because it's not just one model, it's many models. There are some predictions for gauge mediation which follow from general considerations, and so we expect them to be always true, not just for ordinary gauge mediation, but from general considerations. So one of these I've already talked about, the absence of flavor-changing neutral currents. Other predictions, however, really involve the structure of ordinary gauge mediation. For instance, relations among the gaugino masses, or the fermion masses, or what's the lightest particle in the spectrum. These various features we will see turn out to be only true in certain models. Okay, one hint of this, well, there are many hints of this, but one way to see this very easily is to consider a class of models which are just almost trivial deformations of ordinary gauge mediation. I just consider multiple messengers, and I add renormalizable mass terms for them. And then I can study the parameter space of this model, and so that's what we did in a recent paper. And by including the most general possible couplings consistent with the standard model gauge groups, you can already see that some of the standard predictions of ordinary gauge mediation are violated. But since these are qualitative, I mean, we'd like to know what's going on really in detail and in full generality. So that's the question which we tried to answer. Okay, so now let me get to the heart of the matter. In the work I did with Patrick Mead and Nadia Seiberg, we set out to define once and for all what we mean by gauge mediation and to characterize as generally as possible models of gauge mediation using as few assumptions as possible. Okay, so here's what we said. The first ingredient for gauge mediation is that there's a hidden sector and a visible sector, and that the theory decouples into separate hidden and visible sectors in the zero coupling limit. So when we turn off the gauge couplings, there are two sectors which don't talk to each other. Now, a part of our terminology is that the hidden sector includes any messengers if present. So we also would like our formalism to apply to models where there aren't clearly defined messenger fields. These would be strongly coupled models, and where there are fields charged under the standard model in here, but maybe they're not identifiable as messengers. Okay, now to further characterize general gauge mediation, we say two things about the hidden sector, which should always be true. Obviously, it has to spontaneously break supersymmetry, and we'll say that it breaks supersymmetry at some scale m, which could just be shorthand for multiple scales if they exist. But okay, so we introduce a scale m at which the theory breaks supersymmetry. The second ingredient is that it has a global symmetry, call it G, which contains as a subgroup the standard model gauge symmetry when it's weakly gauged. And this weakly gauge is an assumption about the hidden sector, which is that at scales where supersymmetry is broken, the gauge couplings of the standard model are weak compared to whatever other dynamics is happening in the hidden sector. Okay, so our strategy for analyzing this class of models in generality is to start by analyzing the hidden sector at zero coupling, and we'll just assume for simplicity U1 global symmetry. And so at zero coupling, all we have to do is the hidden sector is completely decoupled, and it suffices to analyze that. So, of course, the natural objects to study, all we're told that we have is some theory which breaks supersymmetry and which has some global symmetry. So, and we're not told whether it's weakly or strongly coupled or what the Lagrangian is. So pretty much the only thing we can study are the global currents and their correlation functions. So the philosophy is to try to understand general properties of the theory before we know the underlying Lagrangian. And so in that respect, it's sort of similar in spirit to what people were doing before QCD was accepted, and what we had was current algebra. Okay, but this is just an analogy in spirit. Okay, let me tell you a little bit about these global currents then. Since this is supersymmetry, they fall into a supermultiplet. This supermultiplet is known as a real linear supermultiplet, and in superfield notation, it looks like this. So it's some J, field J, which is defined by this equation d squared J equals 0. And since it's real, that also implies d bar squared J equals 0. So this defines the whole superfield, and in particular, it implies current conservation. So you can think of this d squared J as the SUSY generalization of ordinary current conservation. So in components, you can work out what J is, or you can just look it up in Weinberg volume 3 or something. And so this is what it is. Let me just focus your attention on these four pieces here, the lowest components. These are the only independent degrees of freedom for the current superfield. And J mu here is, of course, the ordinary current, which satisfies d mu J mu equals 0. So these guys here, little j bar, and capital J are the superpartners of the ordinary bosonic current. Okay, so now that we have the current superfield, of course, the next thing to study are its correlation functions. So the non-zero two-point functions, that's the simplest case, these are constrained by Lorentz invariance and current conservation. That alone is enough to tell you which ones are non-zero, and moreover, you can constrain the index structure of them in the usual way. So let me just focus your attention on the main actors in our story here. There are these three fields here, these three functions of x here, which are real, C0, C1/2, and C1. They are real, and B here is complex. Okay, so these are going to be the main protagonists in our story. And remember, keep in mind that the scale m we introduced as a scale of SUSY breaking in the hidden sector, but more generally, it's just any old scale you want that we need for dimensional analysis. Okay, so there are a few more things we can say about the current. In the supersymmetric limit, you can show that the different 2-point functions are related to each other in this way, and that B, this complex one, is 0. So you can just show this using the algebra. More generally, since we're supposing a supersymmetry is broken spontaneously, we expect that at short distance it must be restored, and that's the statement about the 2-point functions, which is that they limit as x goes to 0 to the same number c, and then b limits to 0. And it's important that these 2-point functions are all regular as a function of x. Correspondingly, in momentum space, if we Fourier transform, we get a log divergence at large momentum for the c tildes, but not for the b tilde. Okay, now we're ready to couple our hidden sector to the visible sector. That's the next step. We do that by weakly gauging our global symmetry, which is still a U1. So this is how we weakly gauge a global symmetry. We just add the vector superfield coupled linearly to the current superfield. And the dot dot dots represent various contact interactions that are determined by gauge invariance. Okay, so now we can, at least formally in our heads, integrate out the hidden sector exactly. So that's the goal. So by exactly, I mean that we compute all the 2-point functions, 3-point functions, et cetera, and we imagine doing that to arbitrarily, so we imagine computing those exactly. However, since we're assuming that G here, the gauge coupling, is small, we can still work perturbatively in G, and then we can extract what's the effective Lagrangian at order G squared so we integrate out the hidden sector, and all we're left with is the gauge fields and the gauge supermultiplet. So our effective action is for the gauge supermultiplet, and it just looks like, at order G squared, it just looks like this, where we use the 2-point functions that we mentioned before to get all these quadratic terms in the Lagrangian. And keep in mind, this is a function of p squared, so it really involves all the derivatives. It's not a low energy effective Lagrangian. It's really has all the information at this order in G squared. Okay, now we can read off a few things about this Lagrangian. So the first is the beta function. When we integrate out the hidden sector, since it has fields charged under the U1, we expect that the U1 beta function changes. So that's this statement. If we stare at these terms here, which are the kinetic terms basically for the gauge field, and then we remember that all the pieces of C tilde are the same at large momentum. Well, they have the same dependence on the cutoff, so there's some common number C here. So now we see that the beta function is this number C that the existence of which we deduced earlier. So C is the hidden sector contribution to the beta function. We can further read off at tree level another fact about the visible sector, and so that's the gaugino mass. So we see here the gaugino mass is trivially follows from the form of the effective action is just this term evaluated at 0 momentum. So what we're saying basically is that the gaugino mass is given by some 2-point function of the currents of the gauge of this global symmetry, which is weakly gauged. So that's the formula for the gaugino mass. And then the fermion masses are obtained by doing loops of these gauge fields. If we imagine there's some fermion field which has charge, say, +1, that we add to the theory, then the way it knows about supersymmetry breaking is because now the kinetic terms for the different parts of the gauge supermultiplet are different. So we get these different diagrams here which don't cancel, and which leads to this formula for this fermion masses. Okay, so from this it's straightforward to generalize to SU3 times SU2 times U1. So that's what I'm going to do now. So instead of just a U1, we have 3 different gauge groups. So we have 3 different gaugino masses, and they're each given in terms of their own 2-point function. Okay, so this says that now we can start extracting lessons from this. This says that there are 3 independent complex gaugino masses in general. So this says that gaugino unification is not guaranteed. This is one feature of ordinary gauge mediation, which doesn't seem to survive in the general analysis. And also this is interesting because while we say that gauge mediation is nice because it automatically has no flavor problem, we also have to worry about, in supersymmetry, introducing large CP phases, which are also highly constrained by experiments. And some of these CP phases can enter in through the complex gaugino masses. If they don't all have the common phase, then we could be in trouble. So that does general gauge mediation have, in general, a SUSY CP problem? That's something to think about. Okay. Now, we can also go on to look at those fermion masses. So that's just given by straightforward generalization of what I had before for U1. It's the same linear combination of the currents. And I probably should have said that it's as one check, you can check that this linear combination of currents has to vanish when supersymmetry is unbroken. Supersymmetry tells us that C tilde 1 is equal to C tilde half is equal to C tilde 0. Okay, so this is the obvious straightforward generalization from before. We just sum over the 3 different gauge groups, and we have to have this group theory factor there, which should be familiar to everybody. Okay, now we can start to learn lessons from these fermion masses. First of all, the first comment I want to make is that these fermion masses involve some supertrace-like quantity with different signs for the different terms. So they're not necessarily or not obviously positive. In all the examples that people commonly study, they turn out to be positive. And so for a while, we thought there might be a theorem that's not obvious from this formula. However, then we found in the literature there are actually simple examples where this fermion mass squareds come out negative. So that's actually bad. That means that the fermions, like the squarks and the leptons, would be tachyonic, and then color and charge are broken if they condense. So anyway, you can find already in the literature examples where this quantity A is manifestly negative for all values of the couplings in the model you write down. So the simplest example we found was a model where supersymmetry is broken basically by an FI model with some extra U1 prime, which you charge the messengers under in addition to the standard model. So if you just work out the messenger mass matrix and then calculate this fermion mass squares in this model, which is what these people did, you find that they're negative. Okay, so there's no theorem. The second comment I want to make is that from the form of this, this integral, you see that the typical momentum in this integral there's only one dimensional scale that we've introduced here. That's what we called m squared. So that tells us that the typical momentum in this integral, which determines this fermion mass squareds, is order m. So that means that you can't calculate this fermion mass squareds in some low energy effective theory where you've which is valid below the scale m, where you've integrated out the hidden sector. So you need the full hidden sector to get this fermion mass squareds. Another comment I want to make is that in general, this fermion mass squareds should be finite. So you already see that's guaranteed so that places constraints at large p on this integral. It's nice to see that at the leading order term, which is log p, has to cancel by supersymmetry. But that also tells us things about order 1 over p squared, which aren't obvious from supersymmetry. Finally, and this is the main point for general gauge mediation, we see that there are 3 independent real parameters here, which means that these are parameters which are in principle independent of the gaugino mass 2-point functions that we had before. So we see that the fermion masses are not tied to the gaugino masses, nor are they really tied to the gauge couplings, since for each gauge coupling I can presumably cook up a model with with whatever value of AR I want. Okay, it's actually interesting to try to do this, but this is all the structure of the theory seems to tell us. Okay, let me also mention quickly mention another result which will appear soon. We noticed that there's actually a way of rewriting these formulas which is very suggestive. So we found that we could write this complex two-point function b of x as two supersymmetry transformations of this j of x, j of 0, and then we could rewrite, morally speaking, what's the linear combination of two-point functions that appears for this fermion masses as 4 supercharges acting on j of x, j of 0. So as a check, you can see that both of these correlators have to vanish when supersymmetry is broken, and that indeed happens. When supersymmetry is unbroken, which is indeed what happens. And this is suggestive of relations in ordinary gauge mediation, which say that the gaugino masses are like 1 power of the SUSY breaking and are holomorphic, whereas the fermion mass squareds are holomorphic times anti-holomorphic and go like gaugino mass squared. So, and perhaps there's connections of this to some recent work by other people on the small SUSY breaking limit of general gauge mediation. And okay, I'll skip this comment. So another thing which, so one other general fact about general gauge mediation that we were able to extract, aside from this counting of parameters, are a couple of sum rules that the fermion masses have to satisfy. Now these sum rules have been derived they have a long history, so I won't even try to repeat it. And so they're well known to people. However, I think their generality perhaps was not fully appreciated. So the sum rules just follow from simple considerations. If I remind you, in the standard model, there are 5 different types of fermions, right? So there are 3 different quark fields and 2 different lepton fields. So there are 5 different fermion mass squareds per generation. But we see that the most general parametrization of them is in terms of 3 real parameters. So there must be 2 relations per generation. A quick way to derive these relations is to notice that since this is a quadratic Casimir and the U1 symmetries of the standard model, there are 2 U1 symmetries of the standard model that are anomaly free, then that immediately implies that the relations must take the following form. Okay, so again, these relations have been derived in the context of various gauge mediation models, but here we see that they're fully general. And of course, these relations are meant to be valid at the scale m, at the scale at which we integrate out the hidden sector, and then small corrections, you can show that there are small corrections from a normalization group flow down to the weak scale, and also electroweak symmetry breaking. Okay, so now let me conclude with a summary. We've constructed a framework, which I hope is just a starting point for analyzing general models of gauge mediation, by which we define to be arbitrary hidden sectors which break supersymmetry spontaneously and coupled to the MSSM via standard model gauge interactions, and only coupled to the MSSM via these interactions. So we've used our framework to understand some of the general predictions of gauge mediation, and we counted the parameter space and came up with the following. So we have 3 complex parameters which basically parameterize the gaugino masses, and 3 real parameters which parameterize the 5 different fermion masses per generation. So our framework is suitable now for analyzing strongly coupled hidden sectors. That's sort of why we worked in terms of currents and things. And one step in this direction was recently taken by these people in the context of n equals 2, strongly coupled gauge theories. Okay, another question which, as part of the outlook, which is something we're interested in, is can you build simple models of gauge mediation, weakly coupled models, models with spurions, whatever, which cover the entire parameter space of gauge mediation? So which cover this 3 complex plus 3 real dimensional parameter space. And if so, if you can get such a model, then you can ask what is the minimal construction? So these people recently exhibited generalizations of ordinary gauge mediation with more fields that have the right number of parameters, although it's not clear that they can actually cover the entire parameter space. So there's still something to do here. Finally, a few other things I can mention. It's interesting to wonder whether you can bring the technology of ADS-CFT to bear on any of this. This is something which Herman talked about, but I think there's a lot more to be done, and perhaps in more generality, it's possible to discuss these issues. So in other words, currents and their correlators appear naturally in the ADS-CFT correspondence. One thing we like to study are strongly coupled hidden sectors, which the ADS-CFT correspondence is good at. So maybe there's something to do there. And then finally, there's this nagging problem of gauge mediation that bothers phenomenologists to no end, which is called the mu-b-mu problem. I don't have time to explain this, but in our paper, we tried to translate existing approaches to the mu-b-mu problem into this general gauge mediation formalism, but the formalism has yet to teach us something new about the mu-b-mu problem. That was one of our hopes. Okay, so I hope I've convinced you that it's interesting to think about general models of gauge mediation and beyond the standard model of physics, and hopefully we're trying to get as prepared as we can for the LHC, but time is running out. Not much time left to get all of our stories straight, and the LHC is coming, I think, and it'll put many models to the test. That inspires fear and apprehension and also excitement in those of us who build models. And so I thought it'd be appropriate, also since we're in the Alps, it's close to Austria, maybe to leave with this inspiring image. Yes.
Would anybody like to add to the fear and apprehension with some good questions?
There is another sub-parameter, which is the trilinear scalar coupling, the A parameter. The normally in gauge-mediating models is small.
Yes.
In this more general formalism, you can say something about the A parameter is still small. Why is it so? Why is it always small, even when you go to such a general scheme?
Yes, so that's something we claim in our work, is that it's always small, pretty much no matter what you do. So which you can see this by studying the various two-point functions and their generalizations. So small A terms and is one which we would say is one general prediction of gauge mediation, which might be unfortunate for the Higgs.
Yes.
The reasons to believe that believing that your general prediction will be stable against the introduction of the additional ingredients you need to solve the frequently mu problem.
Right, so all the claims I tried to make here were meant to be insensitive to the additional degrees of freedom that we would have to add. Those would tend to affect the Higgs mass parameters, mh up squared, mh down squared. And there are the sum rules, for instance, that for the third generation could be sensitive. Will probably be sensitive to whatever you add to solve the mu problem.
Come on.
Continuing the question that was asked, it seems potentially likely that solving mu on the mu problem must relax the assumption you're making for GGN, because your assumption that G is 0, supersymmetry is not broken, is not communicated to the sector, therefore mu would have to be 0.
Yes.
And that would be a too strong a statement, and therefore you definitely want to relax that condition if you want to get the mu problem.
I couldn't agree more. So in fact, that's in our paper. I just didn't have time. So one thing we try to do is to generalize our definition, take this as a starting point, generalize our definition to say that not just the gauge coupling is going to 0, but also various additional couplings going to 0 decouples these sectors.
I knew that, there must be some given the question.
Yeah.
Yes.
At one point, there were claims that large anomalous dimensions in the hidden sector could give rise to running. There was a specific model or quasi-model, I guess, like Martin Schmalz, for instance, was one of the people associated with it, that claimed that large anomalous dimensions in the hidden sector would solve the mu and b problem. And I mean, I thought that this whole framework was an attempt to kind of generalize that sort of situation. But now you're saying that, what was wrong with that model? Why didn't that
No, I tried to say that, you know, we tried to translate existing approaches to our framework, but our framework is, we haven't shed any new light necessarily on, we haven't gotten any new solutions to the beaming problem yet using this framework, and that's, I think, something which holds a lot of promise potentially.
But you're not, oh, okay, you're not saying that it can't be solved in general case?
No,
Okay.
I wasn't saying.
Anybody else? Let's thank David again then.